Hello, and welcome to another episode of the Code Breakdown. I'm your host, Andrew DuPont.
And I'm Brian Miller.
Brian, what are we going to be talking about today?
Well, today's a little bit of a divergence from the stuff that we've been talking about in the past. We've been really focusing on Ruby testing, but after some discussions with you, I think we should focus on one of the tools that we use all the time, and that would be Git.
Awesome.
And it's kind of this ongoing discussion that Drew and I have had about how best to get people kind of to a level where they can be really productive with Git. We've had a lot of conversations about this, and one of the things that we think is kind of one of those fundamental issues that we run into a lot is that we find that a lot of devs don't really understand kind of the under the hood aspect of Git. So we wanted to run through just at a real basic level what the data structures are. And I think you were going to start this off.
Sure, yeah. So the most core concept of Git, kind of under the hood, is a tree, and everything in it is a node. Every commit represents a node, and each commit really just holds a diff. So right here we're looking at Snapdragon, which is an open source project that I work on, and we can see at the top where it says C708EF2. That is the topmost commit. And we can see that there's a label of head and a label of real parser next to it. Head is a label that points to the current commit that is checked out. So that just happens to be the commit that I'm checked out on. But if you walk down and you look at the line below that, you can see that that's the parent of the C708 commit, is the E5BC commit. And that's the commit where I bumped the version to version 0.1.12. And then if you take a step before that, you can see there's an actual merge commit. And you can tell that because if you go down to the fourth line from the top, you can see that there's another commit that's kind of off to the right that diverged from its parent before that, which is the 2379. So at some point, it looks like Tim Payne branched from the 2379 commit, and then I merged his change into master, and that created the 9B61 commit. So that's kind of just, you can see that the entire thing is really a tree built up all the way from an original commit which had no parent basically, and you can see all the way at the bottom I have a commit down there which is the 6876 commit that is labeled initial commit, and basically that's the only commit in the tree that has no parent. So basically that's the general concept, is everything's a tree. So if we look right now, we've created, at least for this episode, we created a Git repo, and it contains 2 commits right now, and it's completely linear. There's just one commit and then another commit that follows it. So we have a really simple tree at this point. So let's start looking into the actual contents of commits. Brian, which command do you use to look at the details of a specific commit?
I'm always very partial to show.
Okay,
And I was looking a little while ago. There's this really cool switch. It's pretty equals raw, and it'll show you just everything having to do with a commit.
pretty equals raw, and then we can check out that A01ADDF.
Yep.
So one thing you'll notice is that commits, or you'll hear people say, is commits are cryptographically significant, and because they're cryptographically significant, the summation or the collection of them is also cryptographically significant. The reason that is because every commit is represented by a SHA-1, which is a hash that's composed of the actual commit's content. So if the content of that any of those commits ever changed, the SHA-1 for it would be different. And therefore, like, if there was a security attack on some host that had this Git repo and another person had the copy of the Git repo, they would be able to tell that at some point it diverged, right? If those contents had changed. But if we're looking at this commit right here, we can see that when we did the git show pretty raw, it shows us all the details of the commit. The stuff at the very bottom of the show is really a diff, and it's a specially formatted git diff format. But you can see that we added a bunch of lines to outline MD, which is the markdown file for the outline for this episode. And then above that diff section, you can see where it says added initial outline for the episode. That's just the brief summary description that I added as the commit message when I made the commit. It also recorded that I was the committer and the author, and that it's part of this tree. And we're just gonna breeze over the concept of tree objects right now, because that's not really crucial in understanding this kind of core concept. It's a whole nother layer deep, and it's not really critical. And then there's the commit, of course, which holds the SHA-1.
So I kind of love how this is actually just a diff against dev null.
Yes. It's
So I mean, so essentially you always just start with a diff against nothing, which is essentially the that first commit.
hmm
But so what happens if we want to? What does another commit look like after this point?
So after this point, we can see that if we do the same thing, but look at like the 523 commit, and actually tidbit of information is, um, I think you need 4 characters a minimum of 4 characters in your SHA descriptions. And as that'll work as long as those 4 characters are unique. In the case where those 4 characters aren't unique because there's another SHA that clashes, then it'll force you to add more specific or more characters to make it unique. Um, so it just makes working on the command line a little bit easier instead of having to type the entire SHA-1 of a commit when you're interacting with it. But if we're looking at this one, we can see that this one has one additional field in comparison to the other one, and that is right below the line where it says tree. We can see that there's a line that says parent A01ADDF0F, and that is the SHA-1 for the commit that we looked at before. So we can see A01ADDF0F. So the interesting thing, and one of the very important things to note, is that as I said before, each commit has a SHA-1 that identifies it, and that SHA-1 is composed of the contents of that commit. And if we look at this, the contents of this commit include its parent reference. Therefore, it's cryptographically significant not just in terms of what the diff is that's here, but it's cryptographically significant in terms of how the actual tree is composed and which nodes have which parents, and so on.
So I see that there's a tree identifier there. Can a commit belong to more than one tree?
Can a commit belong to more than one tree? Yes. A commit can belong to more than one tree. But the question, well, I guess the question is, how are you thinking about commits?
Well, that is kind of what we're talking about.
So if we're being 100% pure in terms of our speaking, a commit is a SHA-1, right?
hmm
So in that case, the answer would be no, right?
Well,
Because a SHA-1 would change if it was associated to a different tree because that's the contents of that commit. Does that make sense?
So let's talk about a commit being a reference to the diff or the series of diffs.
The series of diffs. Okay. So
Or
if the commit if you're talking if you're talking about the commit being the diff itself, ignoring the concept of the other pieces of data inside of it,
yeah,
then you can have that same change in multiple trees.
okay,
But do note that even though those diffs are the same, right?
yeah,
In multiple trees, the SHA-1s for those commits will be different.
yeah. So this is when things like patches and can be used to move commits between trees, right?
Yes, exactly.
Okay.
And you can. This also happens when you do things like cherry pick or rebase or many other commands.
All right. So, and we would do those between branches,
We
which is
would.
another, which is kind of something that I want to talk about a little bit.
Okay.
So, one of the other really powerful things that I love about Git is this idea of branches, and it's one of those things that dawned on me a while ago that I mean it's that really all a branch is and is equivalent to a tag. It's just a label that you associate with a commit,
That's
and it's
correct.
just used for identification. And really, honestly, the only thing that Git uses internally to manage the state of a tree is that concept of head, which is just if you think of it like a file pointer to some degree that Git uses just to track where the last commit within a tree is, so that it can know when it switches branches where it should go, and then trace back to figure out what its history is.
Mm-hmm.
So I mean, it's just really interesting because it Git just uses those names to essentially resolve to an actual commit, and that's all Git really cares about. It's just that commit identifier.
Yeah. In actuality, I mean, you can even see that if we look at our tree right now, you'll notice we have master and head, right? Like you were
Yep.
saying. Our tree is super simple. It's just we have our origination commit, and then we have a commit that is a parent that has a parent of that commit. But if we look inside of this hidden folder, this .git hidden folder, and it's not recommended that you actually mess around inside of this folder. Um, but if you look inside of here, you can actually see that there's a branches directory, and there's this refs directory. So if you look in the refs directory, you can see that it has refs heads and tags. If we go to heads, you can see that there is a file called master. And you'll have to ignore my fatal error. That's just because I have some special sauce in my Zesh prompt that's complaining. But you can see there's this file called master, and if we cat the contents of master, we can see that it spits out just the SHA-1 of 523EC. So if we go back to our Git repo and we git L, we can see that 523EC is the same commit that master points to. So the way Git internally manages branches is it really just has a file that has as the content of that file the SHA-1 for the commit that branch points to, and the name of the file is the name of the branch.
So when we think about the difference between branches and tags, it's really just that a tag is meant to be somewhat immutable. I mean, you don't necessarily have to treat it that way, but it's definitely recommended to not. And a branch is designed to be it has its own concept of head.
Mm-hmm.
And so when you switch into it, it's designed to have a series of commits that are in it that you can use to compare to another branch, and to interact with those two things as their own separate branches of the tree.
Yeah, from a technical standpoint, tags and branches are basically implemented the same way. If
Yes.
I tag foo, um, we can see I just created a tag foo on the latest commit, and if we went into git refs tags, there's foo, and I can cat foo, and it's 523 EC because that's the commit I just tagged. Now, the way to think about it is really just their tags are meant to be immutable. They are not meant to be moved, and it's really, you can get into some really nasty messes if you try to move tags. So best practice is generally if you've created a tag on something and you've pushed it up to another repo, like a central repo if you're using a centralized model, or even if you've shared it with anybody in a distributed model, um, you do not want to delete that tag. It's better for you to actually just create a new tag with a new revision,
Yep.
because you need to change something.
And that actually kind of brings forth some of the issues that you run into when you fundamentally change the structure of your tree when doing certain operations. And I know that's something we're going to definitely dive into the next episode where we cover things like rebasing and some of the other features that are available when you want to start manipulating things.
Yeah, definitely.
So I think that we've given a good overview of the data structures that are in Git, and we will go into more of the, like I said, the tree manipulation stuff in the next episode.
All right. See you next time.